Hello, everyone. Welcome to lecture 16. Today's topic are these. So we'll continue with distributions. We saw five distributions so far. I will show you some examples of problems where you would like to solve using distribution, and we would like to compute the expectations, so the average value of these distributions, and we will then look into something called variance. Variance is a measure of spread in the data. So you may have seen variance and standard deviation, but yeah, we will try to define and work through some problems, and then I will also describe so-called moments or higher order moments. Okay, so let us continue with so let us solve some problem from Poisson distribution. Let us say we have a problem where we want to send a bit string of length n equals to 10 to the 4. The probability that a bit can be corrupted is given to be 10 to the minus 6. So the probability is very low that the bit, a given bit will be corrupted. The question is, what is the probability that the message will arrive uncorrupted? Okay, so this is the problem we have. We want to send a bit string of length 10 to the 4. The probability that a bit can be corrupted is 10 to the minus 6. What is the probability that the message will arrive uncorrupted? Okay, so how are we going to solve problems like this? So in this case, you see n is 10 to the 4 and p is 10 to the minus 6. And you may want to solve this using a binomial. It's tempting to use binomial. Who is this guy? Sai and something. Why are you bothering me? I keep a note of who tries to bother me, right? If you have question, you just unmute your microphone and ask question. That's it. Okay, so so how we will solve problems like this? Okay. So you will be tempted to solve this problem using binomial because you see this n and you see this p. Okay, so it could be written as binomial of n comma p. Parameters are there, right? But this is an example where I would like to say that sometimes you may use Poisson and not binomial, especially in those cases where n is very big. So in this case, n is very big. Okay, so let us say this denotes that n is very big and p is like very small. So where p is very small. Okay, so sometimes very small and very big is denoted like this. So so in this case is I can use Poisson, okay, because when we derived Poisson, we saw that Poisson is a approximation of the binomial, is a good approximation of the binomial when n tends to infinity and p is small, okay, small enough. So this is a case where instead of binomial, because binomial may not be that easy, so in these cases you may get away with Poisson. So this is one of those examples where I will instead go ahead and use Poisson. So in the Poisson, we know that lambda is n times p, so which is 10 to the 4 times 10 to the minus 6. So we know what it will be. It's like 0.01, right? So this will be Poisson. Okay, so x is a Poisson distribution with the parameter 0.01. Okay, and let it denote the number of corrupted bits. Now Poisson PMF we have. Okay, so this is the advantage now. Given a problem, we know which category it belongs to. And for that category, the PMF is known, or you can look up this PMF from a book. and then you can solve your problem. So in this case, I want to know that the probability that the message will arrive uncorrupted. So this means that there are no corrupted bits. Okay, no corrupted bits. That's what it means, because X is the number of corrupted bits. So for no corrupted bit, I need X is equal to 0. So here I should put X actually. Okay, so that's the Poisson PMF that you recall. Okay, so X is like the small x, right? So but in this case, since I have defined X to be exactly 0, now the proper way to do this is like immediately put 0, because I have already said that small x is 0, right? So in the Poisson, I should put this 0 immediately. So if I do this, and lambda is 0.01, so that is 0.01, and this is x, and this is x factorial, and e to the minus lambda. Okay, so this is again lambda. So if we do this calculation, then we get this, which tells us that this is 99% probability. Okay, probability that the message will arrive uncorrupted. So that's a pretty like good, pretty good probability for us. Okay. So there is an area, it's called error correcting codes and so on. Maybe I will build some tutorial around that, and then you will see how probability is used in coding theory. Okay, and also let us say in quantum algorithms, right? So there are few things I have in mind. I am trying to prepare some nice assignments with some applications in mind. So that will come later. Okay. So what I said before is this. So binomial is, so X could have been seen as a binomial. Okay. Binomial with N and P. And so binomial was like n hats, let us say, okay, k hats. What is the probability of seeing k hats in n trials, right? So in this case, you might ask, what is the probability of seeing 0 bits, that is, you want uncorrupted, so 0 bits among 10 to the 4 bits, right? So you could have applied binomial, but in fact, as an assignment, you can try and see why whether you get similar answer or not. Okay. So when to take a takeaway from this example is that when n is large, p is small, feel free to use Poisson in a real life case, but in the exams I may tell you that no, you must use Poisson or you must use binomial sometimes, but sometimes you may not, but still you can get a good enough approximation. So in real life you have to decide when to use Poisson and when to use binomial. Another example of Poisson, this is a more straightforward example. So this is the classic example. So Poisson distribution is often used to model the number of events that occur independently at any time in an interval of time or space. Okay, so this is what we know. Okay, so and with a constant average rate, the earthquakes are a good example of this. So let us say this example with an earthquake. Suppose there are an average of 2 to the 2.8 major earthquakes in the world each year. Okay, so let us say 2.8 major earthquakes happen in the world each year. Okay, on average every year. What is the probability of getting more than one major earthquake next year? So what is the probability of getting more than one major earthquake next year? So you can think about this, and these are the cases where the problems that ask you probability of something happening in an interval of time. Okay, that's a very classic example of Poisson problem. Okay, so this is one of the case, like in next year, 1 year is an interval, and there you are supposed to find the probability of a number happening, right? Some number. So in this case, the number of probability of the getting more than one earthquake. And this is a classic example. So you can guess what is the Poisson for this, right? So Poisson, the average goes into the Poisson. So this is like Poisson, and then 2.8 with the parameter 2.8. Okay. So and X is the like the number of earthquakes. Okay. So X is the number of earthquakes, and with this we can go ahead and solve this problem. Now, what we are asked here is probability of getting more than one major earthquake. So what we are asking for is X greater than 1. Okay. So X is the number of earthquakes. This denotes the number, okay, number of earthquakes. So what we are asking for is what is the probability that X is greater than 1. Okay, so this is the setup. So X greater than 1, we can write this. So this partitions our sample space into two parts, X and X complement, right? So this is like 0, 1. So these are the valid ranges for X. Range of X are, it can be no earthquake, 1 earthquake, 2 earthquake, and so on. So X greater than 1 is this part. Okay. So X complement can be like the probability should be sum up to 1. So probably the X greater than 1 can be seen as complement of that. So that will be like 1 minus probability that X is equal to 0 minus probability that X is equal to 1. So that's what we can conclude from here. Okay. So it boils down to computing these two cases using Poisson. Okay, so when someone gives you a question like this, then try to see if you can take a complement and reduce it to some cases like this, where you have like finitely many terms to compute. Okay, so this is what we have. X is a Poisson, and then we want to compute this. And probability that X greater than 1 is 1 minus probability that X equals to 0, X equals to 1. Now we know the PMF of a Poisson, so you will use the PMF of Poisson and just go ahead and compute this. So this guy is this, and this guy is this. Okay, so it's a very simple algebra, and then we do this and we get some number which in terms of percentage, this is like 77% probability. 77% probability is or close to 80% probability that there will be more than one major earthquake next year. Okay, remember that we are not telling how many earthquake, but we are asking for probability of getting more than one. Okay, so so this is what we have. Okay, classic example of Poisson. So let us now compute expectations of some distributions. So what is the, on average, what do we expect, right? So that's the expectation, the mean or the average value. So this is the Poisson distribution we have with parameter lambda, and PMF is given by this. Rx is the range of the random variable X. And we are asked to show that the expectation of this Poisson variable is lambda. Okay. So we know the formula for expectation, right? So how do you recall? The formula for expectation is for the discrete case, it's sum. For the continuous case, we will see that it will become an integral. Integral is the sum of is the generalization of sum, right? So here in this case, it will be P and then probability PMF of X, the random variable X. So this is the definition of expectation. And PMF is known to us, which is given here. And then we just have to find this sum. So this is a proof that the expectation of X is lambda. So this is the PMF of random variable X, and we have to multiply it with X. And then if we do that, then X e to the minus lambda. And so basically the 0 term can be neglected because first term will be 0. So I can start with 1. And then e to the minus lambda can be taken out. So this is where e to the minus lambda, because it has no dependence on X. So this becomes lambda x, and then x and x, 1x gets cancelled. So this becomes x minus 1 factorial. And then I can substitute x minus 1 is z. Okay, so then if we do this substitution, then we have x minus 1 is z, and then here in place of x I have z plus 1, and then lambda can be taken out, one lambda can be taken out, and then we have lambda e to the minus lambda, and we are left with this term. What is this term? So from real analysis, what do you know about this term? So what is this term? This is, can you tell me what is this term? Chat is frozen, not yet. It is frozen somewhat, as usual. I mean, you can log into Skype if you want. The chat is as usual frozen. You can always turn on your microphone and talk, it doesn't matter. So what do you think about this sum z equals to 0 to infinity lambda to the z by z factorial? Okay, this comes from the Taylor's expansion. So this is like Taylor. What is the Taylor expansion? So recall calculus or real analysis. So what does this mean? So if f from R to R is infinitely differentiable, then f can be expanded. Okay, I'm using the word expanded around x equals to a, using this f of x is f of a plus f prime of a by 1 factorial x plus dot dot dot, right? F nth derivative of a by n factorial, and this would be x minus a. This would be x minus a to the n plus dot dot dot. Okay, so you need infinite differentiability because in the series you need arbitrary derivative. Okay, so this is like the derivative with respect to x of the function, right? So this is the Taylor's theorem in real analysis, and this seems to be the expansion of e to the x, right? So e to the 0, that's expansion of x around origin, right? So e to the x can be written as e to the 0 plus derivative of e to the x is e to the x, and then it is like e to the 0 by 1, and expansion is around x is equal to 0 in this case. Okay, so this is like x minus 0, this is x plus e to the it's always e to the 0, and then here it's like x squared by 2 factorial plus dot dot dot. Okay, so x to the n by n factorial. So this is coming from the Taylor series, so this is of this form. Okay, so in this case it's like in place of x you have lambda, so this is like e to the lambda. Okay, so this is e to the lambda. So e to the lambda and e to the minus lambda gets cancelled, and then you are left with lambda. Okay, so that's the expectation of a Poisson. Now let us compute the expectation of a binomial distribution. So binomial expectation so that it's NP. Okay, so so that it's NP, where x is binomial, p greater than 0 less than 1, and the PMF of binomial is given by this. Right. So how do we show that the expectation of a binomial is this. So we have calculations. These are like simple algebra. So it doesn't need, it just needs a little bit of manipulation. So let us see this. I want to compute expectations of the binomial. So I will put the PMF of the binomial. This is the PMF. And X will be there. That's how the expectation is like, X times PMF. So that's what we did, and X is here, nx, px, q, n minus x. So I started with 1 because the first term is 0. Okay, so the first term. So additionally, we note here this identity which we will use here. Okay. So what we observe is this. For what is this we want to calculate, right? This term here. So x n, choose x, is can be written as x n factorial by n minus x factorial n factorial. This is just expansion of n choose x. So this is n factorial, and x gets cancelled here. So we get x minus 1 factorial. And this is nothing but n. So you just take one n out. So this will be n minus 1 choose x minus 1 formula, right? So this is what we will substitute now. This is what we will substitute here in x and choose x. So this is what we did here. And then we substitute x minus 1 equals to z. Okay, so we substitute that, and that's what we have here. So z goes to 0 to from 0 to n minus 1, and then in place of x I have z plus 1. In place of x minus 1 I have z, and this, and I can take n and p common. So take n and p common, and the remaining term will sum to 1. Okay, so if the remaining term, you can prove that it will sum to 1 after you take n and p common. So the final result will come out to be n times p. Okay, so this is where we have the expectations calculated for a binomial. Now what I will define is some other statistical term. The first statistical term we saw was expectation. The second statistical term is variance. So the expectation value Ex, which is also called the mean or average value of a discrete random variable, is a rather coarse measure of how X is distributed. Okay, so the mean does not tell you more about the spread of the data. Okay, so mean doesn't tell much about the spread of the data. We will see this. So for example, consider the following situation. So let us see, you get 1,000 rupees. This is one case. Second case is a fair coin is tossed, and if it is head, then you get 2,000 rupees. And you consider another event, a number is chosen from 1 to 1,000, and if you can guess this, you get rupees 1 million. So you see, these are different cases, right? So you get 1,000. There is nothing based on chance here. So you get 1,000. That's it. In the second case, a fair coin will be tossed, and then if it is head, you will get 2,000. And then the third case is like one number will be chosen from out of 1,000 numbers. And if you can guess this number correctly, then you get 1 million. Now, if you compute the expectation for this, you get 1,000 in all three cases. In all three cases, the average expected value that you get is rupees 1,000. Okay, but you will agree that your chances of getting any money are quite different in all three cases, because first one is deterministic, right? First one is deterministic. You surely get 1,000. Now on average here also you get 1,000 because the expected value is 1,000, but it's based on chance now because there is half probability that you will lose. And similarly in the third case. So there are variations in these three cases here. Okay. So the three cases differ in the spread of the PMF, and this can be measured by the variance. So now what is variance and standard deviation? Okay. So let mu be the usual notation for expectations of the random variable. The variance of the random variable is defined as follows. It's expectation of x minus mu whole squared. Okay, and once we have this, we know how to compute expectations of some g of x, right? So expectation of g of x is sum of g of x and the PMF of the random variable x. Okay, so this is what we know in general for gx. In this case, you can consider this as gx. So we plug in gx and then the PMF of, so sometimes I use f, sometimes use p of x, or sometimes use f of x. Okay, I will use this interchangeably for PMF. Okay, so this is how I will define variance of x. So what does your intuition say? Well, your intuition is saying like it is checking the spread of the data, because if you are far away from the mean, it will contribute more to the sum, right? So it will far away from the mean, and also this also tells you what are the, I mean, is your data more, if your data is more spread out, then obviously this will get maximized, but it also depends on what is the PMF there. Okay, so the graph could look like this, something like this. Okay, so if you are how far your data is spread. Okay, so some graph could be like this. Okay, so it's like wide variation, right? So you are adding so many of this. This is the mean mu, and then you are subtracting, and then so if you have more variations, then like many of these terms will add up. So this somehow intuitively tells you what is the spread of your data. If your data is taking equal values all the time, then yeah, spread will be like 0, because each time these terms are 0. Okay, so it's telling by spread we also mean like the changes in your data. Okay, so the by spread is not just like, it's also the data values, the variation in the data values. Okay, so if your data values are the same, like in uniform distribution, then the variance will turn out to be 0. Okay, so that's the intuition. And then to get a measure in the original unit, we remember that in the variance we are squaring these terms, right? So to get into the original units, if you take the square root, then people usually prefer to use standard deviation. Okay, that's if you take the square root of this. Okay, so square root will be defined like this, which is nothing but the variance of x. Square root of the variance of x is the standard deviation, and this is the standard notation for standard deviation. So sigma. Okay, so let us compute standard variance. Let us say in a simple example, let us say x be the value of one roll of a 6-sided die, and recall that expectation of x is 7/2. What is the variance of x? So what is variance of x is defined to be expectation of x minus mu whole squared. Okay, so this is equal to sum over all possible values that the random variable takes. So in this case, the random variable takes which values? Right, so 1, 2, 3, 4, 5, 6. Okay, so these are the range of x you can think of, and then we sum over those values of x. So it's the range of capital X, and small x is the values that it takes. Okay, so and so in this case, so x minus mu whole square, right? So this is like x minus, so in this case mu is like 7/2, right? So 7/2. So this is mu, right? So 7/2 whole square, and then we have the PMF of x. So PMF of x, and so for each the probability of each of these happening is 1/6, right? So this is like sum over x minus 7/2, and then times. So this is equal to 1/6. So, and you have to sum over this x equals to 1, 2. So this is like, and this is squared here. Okay, so this is like 1 minus 7/2 squared times 1/6 plus 2 minus 7/2 squared times 1/6 plus dot 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 plus 6 minus 7 by 2 squared times 1 over 6. Okay, so you compute this and you will get the variance that you need. And if you have to compute the standard deviation, then you have to take the square root of this. Now, if we go back to, so what is the motivation for the variance? The expected value, the expectation value of a discrete random variable is rather a coarse measure of how X is distributed. Okay, so we have seen this situation. So this is the example that I'm following up and want to see what are the variance in this case. Okay, so this is an example I discussed before. So let us compute the variance. In the first case, there is only one outcome. And since there is only one outcome, it will be the mean of this will be exactly the same outcome, right? So in this case, the variance will be 0. Okay. And second case, if we see you toss a coin, fair coin. Okay, so it's like you have probability of half. In one case you get 0, in one case you get 2000. So X range of X is this. You get 0 or 2000, and then you get half and half, right? So so in one case you got 2000. Okay, and then subtracting from the mean. Okay, so X minus mu whole square, and in this case also you're doing X minus mu whole square, but here your X is 0. Okay, so other option is 0. So if you do this, then the variance is 10 to the 6. So you see here the variance was 0, but here you have wide variance. Similarly, if you go into the third case, then the variance is 10 to the 9, which is quite big. So this tells us like how widely the third case is. There is a lot of variation in the data. Okay. So let us see some remarks on the variance and standard deviation and expectations. So if you are told that the average starting salary for someone working at the company, let us say statistics is the company name, is let us say 70,000 rupees. Okay, let us say you are like very happy, it's your first job, let us say, and you are very happy with 70,000. But then if someone tells you the standard deviation for starting salaries at company this is 20,000. Okay, then you will be a bit worried because the standard deviation is very big. Okay, so it's 20,000. That's a lot of variation in terms of how much money you can make. Okay, so the average salary. Okay, so the average starting salary someone told you 70,000 is not a good indication of how much you might be getting. Okay, you also have to look into the standard deviation. What is the variation in that? In other words, someone might be getting very high and someone might be getting very low. Okay, initially. So, but if the standard deviation was only, let us say 5,000, then you have a much better idea that it's somewhat like it's not going to be more like it's like plus minus 5,000, something like that. Okay, in that unit. Okay, not exactly maybe, but in that unit. So you may say that, okay, you are not going to be too low than 70,000. Okay, if 70,000 is the average and standard deviation is 5,000, then your salary will be pretty much close. Okay, so without calculating standard deviation, you can't get a handle on whether the data is close to the average or not. Okay, so this so and also standard deviation obviously does not imply same data set. Okay, so same standard deviation does not imply the same data set. For example, the data set this I mean the same okay, there is a problem here. So same standard deviation and same average. So what I want to say is the same average does not imply the same standard deviation, obviously. Okay, because in this case, the data sets this and this have the same average, which is 200, but they have different standard deviations. In this case, the standard deviation is like +1. Okay, and in this case, so standard deviation is like always a positive quantity because it's the square root of variance. Variance is always positive. So it's like +1 there, and then here it would be more than that, a lot more than that. Okay, so yeah, okay, so that was the In the second case, it is standard deviation was 200. So there is wide variation in the data. Okay. So standard deviation can be computed using using this formula, and we derive this formula using using the linearity of the expectations. And this is the calculation for how I can do that. Okay, so let us go through this. These are simple things. Okay, so variance we know is x minus mu whole square PMF of x. We expand this, so this is x square minus 2 mu x plus mu square px, and then we individually distribute the sum. So x square px, 2 mu can come out because there is no dependence on x, so this is x px, and then mu square this. Now this is nothing but expectation of x square. So, and the inside term, this is nothing but expectation of x. Okay, and this will sum to 1. Okay, so you will have just mu square here, and this is like, and this itself is mu. So you have minus 2 mu square plus mu square. So this is like 1 mu square here, minus mu square here, and this is this. So this is the proof of this. Okay, so sometimes it's easier to compute this. Okay, using this. Okay, so other properties of variance are the following: variance of alpha times x. So this is the alpha is some constant. Okay, in our case it's a real number. Then this is alpha square variance of x. So this can be computed like in a straightforward way using the definition. So variance of x plus alpha is variance of x. So if you translate your data by adding alpha to each of the x, like. So in that case, the variance doesn't change, and that is intuitively clear. Okay, the variation in the data won't change if I scale each, translate each data points by some alpha. Okay, so these things can be proved easily. Okay, so I'm not going to like, this is like expected variance of alpha x, right? So this is like expected of x square minus mu x, right? So this is like alpha x. So this yeah, so here I have alpha x, so this will be like alpha x square. Okay, so, and variance of x, okay, let's see, or let me use the original definition, right? So expectation of alpha x minus mu whole square. Okay, so this is also another. So we have to prove that this is alpha squared variance of x, right? So how do we prove this? So we use the linearity of x, right? So we use the linearity of expectation, I mean. Okay, so how do we prove this? So is this equal to alpha squared variance of x? Alpha squared variance of x will be how much? Okay, so alpha squared variance of x is alpha squared. In this case, it's like we have to prove that this is expectation of x square minus mu squared, right? So how do we prove this? And since this is so expectation of x, we have to fix first, otherwise we can make mistake, right? Expectation of x is mu, so expectation of alpha x will be alpha mu, right? So there should be an alpha square here, right? Okay, so either way we can prove like this, all this, it doesn't matter. So the important thing to note is expectation of alpha x is alpha mu. So in the formula, if I put, then there will be alpha squared here. Okay, I take alpha common, and alpha and in this case it was like even alpha x whole squared, right? So alpha square comes out, and e of x square minus alpha square mu square. So that's another way to prove this. And if you take alpha square common, and then it's done. Okay, so it seems like this is easier. Okay, forget about this. Okay, So we can prove this in a straightforward way. Similarly, we can prove this variance of x plus alpha. Okay, so what is the mean of x plus alpha, right? Mean of x plus alpha is, so we'll be using linearity. So this is expectation of x plus expectation of alpha. So expectation x is mu plus, and expectation of a constant is the constant itself. This is mu plus alpha, right? So use this, and then we have x. So this is like expectation of x plus alpha whole squared minus mu plus alpha whole squared. Okay, so you compute this and it should turn out to be variance of x. Okay, so I leave this up to you to do this. Okay, so this is a simple property. And then okay, so how do we compute variance of some, let us say some distributions that we are familiar with? So far we have computed expectation of binomial, expectation of Poisson. Now we are thinking, how do we compute variance of these distributions? So the most complicated ones are the binomial and Poisson. Other things also you can compute for Bernoulli, uniform, and so on. So let us see this. So how do we compute the variance of the binomial? Okay, so this requires a little bit of work. Okay, it's not that straightforward. So let me do this. Work. So the first thing I will need, okay, is, okay, let me start with the formula itself, and then we will figure out what to do. So variance of this, we know, is expectation of x square minus mu squared. So that's the formula for the variance, and we can write this as follows: x minus 1, expectation of x minus 1, plus expectation of x minus expectation of x whole squared. Okay, so you can see that this is same thing as this. Okay, if you expand this, then this is expectation of x square and minus yeah. Okay, let's see. Is this same as this? Not really, right? Yeah, okay. So inside we have one, yeah, this is fine actually. Okay, this is correct, because I need to cancel one expectation of x, right? So this is correct, you can verify. Now, I have done this, and this is a little bit tricky. Initially, you will see why I'm doing this. So these things are known to me because expectation of x for a binomial is NP. So this is known to me. And hence this is also known to me. That's the square of expectation of x. And what is not known is this guy. So this is where our focus is now. And the reason why we did this is because it makes our life a bit easier to, if we can compute this now. Okay, so let us see this. So expectation of x minus 1 will be, if we write this using so it should be x equals to 0 to n, x and x minus 1 and x p to the x 1 minus p to the n minus x. Okay, so this is the binomial with the parameters n, p. Okay, that's what we have seen. So this is where we have the p here, and this is equal to sum over x minus 1 n factorial by x factorial n minus x factorial well, okay, so what we notice here is 0 and 1, these terms will cancel. So I can start the sum from x equals to 2, right? So x equals to 2 to n, and then x equals 2 to n, and then I can write this as n factorial by x minus 2 factorial, and then n minus x factorial. Okay. So it like these things I have like cancelled out from this n choose x. In the denominator I had this x and x minus 1, so I cancelled out. So I start from now x minus 2 factorial. Okay, and remaining terms remain the same, 1 minus p n minus x. Okay, so now I have to go to the next page. Say, okay, so you may not remember this term, right? So I'm going to like write this. So what we had in the previous slide is x equals to 2 to n factorial, and x minus 2 factorial, and n minus x factorial, and p to the x, and 1 minus p to the n minus x. So this was from the previous slide. So what I can do is that I can take n and n minus 1 common. I can also take p squared common. So this means x equals to 2 to n minus 2 factorial by x minus 2 factorial and n minus x factorial. So I've taken p square common. So here I have x minus 2, 1 minus p n minus x. So this is equal to n minus 1 p squared. And let us say I substitute y is x minus 2. So if I substitute y is x minus 2, then and I also substitute m is n minus 2. Okay, so this becomes m factorial on the top, and then y factorial, and m minus x minus 2 is y. Okay, and x minus 2 is y, and I can replace this by m minus y. N minus x is n minus y. So you can see after doing these substitutions for n and y and x, you will see that this is turns out to be m minus y. So p to the y, 1 minus p m minus y. Okay, so again, like I have substituted n minus x to be m minus y here. So this will be equal to n into n minus 1 p squared. Now if you recall the binomial expansion, this is the binomial expansion of p plus 1 minus p to the mth power. Okay, so this is the binomial, I mean, this is the expansion of this term. Okay, it's like a plus b to the m. So this is how it will expand. So this is what I have used, and then this is n minus 1, and then inside what do we have inside? Well, inside term gets cancelled, right? So pp gets cancelled, so I have 1 to the m, so there's nothing left. So I have just this term left, p squared, right? So remember, this was expectation of x and x minus 1. This is what we started with, right? Now we got this term. So now we can write down the variance of x. So variance of x is was expectation of x minus 1 plus expectation of x minus expectation of x whole squared. Okay, so this was the term, and this was the only missing term, and we found that this is n minus 1 p squared plus np minus np. So np is the expectation of x, so this is like in this case squared. So this will be np n1 minus p. Okay, so this is the proof that the variance of the binomial distribution is np and 1 minus p. So it requires some algebra, I would say. Okay. So what I can define next is something called nth moment. So in general, what we have seen is, so in other words, like we can define the variance of higher order. Okay. So moments, you can think of variance of higher order. Okay. For example, you can see that if n is 1, then the first moment is what? X minus mu. Okay. The second moment is n is 2. If n is 2, then I get x minus mu whole square. You can generalize this. The third moment will be x minus mu cube. Okay, so that's why people define in general the higher order moments to see higher degree of variations in the data. Okay, so that's what we remember, that first moment is not necessarily expectation. Okay, so expectation is just this, right? So you should remember that. However, second moment is indeed like the variance, the way we define variance, right? But the first moment is not necessarily expectation. So, okay. So this is how we define higher order moments. And so zeroth central moment mu 0. So zeroth central moment by default is 1, because if n is 0, so the whole thing will be 1. So expectation of 1 will be just 1. So that's the zeroth central moment. The first central moment mu 1. The first central moment mu 1 will be 0 actually. Why? Because of the linearity, because we say that the first central moment will be this, but expectation is linear. So this will be expectation of x minus mu, but this is mu minus mu, 0. So the first central moment is 0. Okay. And the second central moment is called variance. So that's what I said. This is expectation of x minus mu whole squared. Okay. It's like central because we are doing it around the mean. So mean, you can think of this as like a center. Okay. Okay. So a natural question is there a quick way to generate moments? Okay. Is there a way to generate higher order moments in a much quicker way rather than computing expectation of x minus mu to the n? Okay. So that's the thing we are asking for. So that's something called a moment generating function. Okay, so these are the functions that are functions of some variable t, and if you take, and these functions can generate higher order moments. Okay, so moment generating functions are defined as follows: are the functions of some t. Of course, it also involves the random variable because it will generate moment for that random variable. Is nothing but the expectation value of which is this. Okay, so you are given a random variable x. You compute the expectation of e to the tx. E to the tx is some function of x, right? So this is like g of x. We know how to compute g of x. Well, we take g of small x, and then we multiply it with the PMF of x, right? So we can compute this. And once you have this, then the claim is that it can be used to generate moments. Okay, so it is easy to verify that mx0 will be 1 because if t is 0, then these terms are 1, and then this is just the sum of the PMF. So sum of the PMF is 1. We know that. Okay, so first this is verified, and this is like expectation of x can be computed by this. If you take the derivative of so this is like derivative of your moment, and then you evaluate your derivative at 0, and that will give you the expectation. Okay, so we can verify this. Y derivative of this with respect to this will give you, because if you take a derivative of e to the x, then I will get terms like this. Derivative e to the tx with respect to t is this, right? Now, so this is the mxt, d of mxt by dt is this, and this is sum over this, right? Now if I put 0 now, which is the 0 here, then it is nothing but x px x, which is indeed the expectation, the usual expectation. Okay, so this so using this moment generating function, once someone gives you a moment generating function, it's easy to compute the second derivative, and similarly you can generate more. So we will continue with this in the next lecture, how we can define moment generating functions, and using this moment generating function we can define higher order derivatives. Okay, so that will be the topic that we will discuss in the next class. Okay then, so have a nice day and bye.